Hi, this is Silvia Mazzoni, and welcome back to part 2 of my benchmarking HDF5 format. In this video, I'm actually going to start the benchmarking part. You've watched the previous video that gave you the basics about HDF5, and now we're going to be benchmarking on data types. As I said, I've done two types of benchmarking. One is on data types, and one is on data structure. More than data is almost, how do I want to manage it, and where do I want to put it? So what's important in benchmarking is what are the metrics that you're taking into account. Always think about what's your baseline. What are you comparing this to? Okay, and maybe you're just comparing two different things, but I actually have a baseline with ground motion. Right now in the current paradigm, each time series is saved as an individual ASCII file with a header. And I've shown you what that looks like. And a user reads each time series, extracts the time series, the time increment from the header, does the processing, and it reads this time series file. The first 4 lines are headers, and then everything else is just one long time series. Then you can run OpenCs or whatever kind of processing you need to do, and you move on to the next file. And so you're literally working with these data as chunks of data, and that's why I call it data, not metadata. The key options that we have when we have our choices is the data type. Do we store it as ASCII or do we store it as something else? You've got data frames. You've got all these different types of data whenever you're working with your own projects, right? And then how do we structure it? Do we do groupings versus just raw data sets at the root? Or do we do one file versus many files? So these are the options that we're going to be looking at. What are the key performance metrics? Number one for me is file size. Okay, as much as there's plenty of room and things that you can store it in the cloud, there's still going to be limitations on space. It's going to cost money. And so if I can minimize the file size, that is the most long-term gain that I have, because then I can keep these files for as long as I want to. I keep producing so much data, and so if I can shrink the space that it takes, I can just generate that much more data, right? The second metric is write speed. But again, this is computer time. I want to compare it. But that's just, it's a one-time job that I do. It's important and we need to look at it. But to me, this is weighed the least. But I want to know what the difference is anyways, because if it takes 10 times as long to do one type than the other, then that comes into play because I have to do a lot of writing. On the reverse side is the read speed. This is key. Okay, and something that we can't measure, and I've already mentioned before, is memory usage. If you're reading a JSON file or just a CSV file, you got to load up the entire thing in memory, while with an HDF5, you're only reading one object at a time. This is not something that I wanted to benchmark because I was really more interested in, I know I'm going to use HDF5 files, how am I going to work with them? And then the other metric you need to think about is the read, but also the run speed. So maybe, my OpenCs analysis takes so much more time anyways, that the read time may not be key. And remember, you might want to work on parallelizing these as well. 5, which is almost number 1, is how easy is it to work? Is it easier to manage groups and different files? Is it easy to write one type versus another? And then the other performance metric, which is a plus already, it's a self-documentation. And so that's when you have groups and attributes may take up a little bit of space or a lot of space. Let's find out how much it is, because that helps my documentation. So if it doesn't cost me too much to self-document, I'm going to take advantage of it. And so that's what I'm going to be testing in my benchmarking. Considerations are pretty much in these questions. What is the most efficient data type to store? So that's my first benchmark test. And does using groups to structure your data take up more space, time, right? Those are the 3 metrics. And so we're going to test that. Is the loss in performance worth the gain that we have in documentation and easy to manage? Spoiler alert, yes, there's insignificant extra cost in any of those metrics. Opening one HDF5 file versus opening it for each record. And so I'm going to actually be testing this. I'm only working with one file in this case because I'm not working with that many files. So I wanted to test, do I want one big file or many smaller files? So there is the space is obvious, but does it cost more to be opening up many files versus opening up one file and keeping it open? And so I did that in the benchmarking, that I open it once versus opening it for each record. And you'll find out that the extra time is insignificant. So it may be worth organizing your data in different files just to make it easier to manage the data. And so then how do we want to store the data? Do we want to do it in different files for grouping and data management? That's an option. That's a really nice option for some of the applications, because very few people care about the velocity and displacement. So maybe I will give you one file and I give somebody else all 3 files, and different people in different applications now have access to, a smaller file, which is always the best thing to work with. So what are my options? My options that I'm going to be looking at is staying with what I have. Individual ASCII files with a header, different HDF5 files with data sets and attributes either stored as a string or as a NumPy array. So this is my first benchmark. And then the second benchmark test is HDF5 with groups, data sets, and attributes. And I'm going with the NumPy array though, so I'm not doing that comparison while I'm doing this comparison. Okay, and then do I compare 3 and 4 go together, or do I want to have many HDF5? Now we're going to evaluate the metrics, okay? But these are particular to my case. You have to make your choice based on your application and use and even user. What would your user prefer? Well, since we're looking at user and use, let's look at what my use case is. And this is really important because you've got to make sure that what you're looking at is comparable to what I'm doing, and they make the modifications to your benchmarking based on what's important to you. So I'm dealing with a large number of AT2 files. I've got 273,000 AT2 files, as well as just as many VT2 and DT2 files. This is what the files look like. Tiny little files of variable size though. Some earthquakes are really long and some earthquakes are relatively short. And so that's what I'm plotting here in this figure on the left. This is the file size times 10 to the 6th. So this is megabytes. So some files are 3 megabytes, while some are 1 megabyte or even much smaller fractions of that. So all my files are all of variable length. I've shown you already these files before. There's a header at the very top where I want to grab the data, and then the time series that has been written out in rows, but it should really be one long column of data. So the very first benchmarking test that we're going to do is going to be on data types. If you see in this figure, you think it's a sunset, but it's actually a sunrise. So you got to make sure you understand what the data is and how you can work with it. So what we're going to do, we've got different data types or different ways that we can store our data. Remember, it's just our ASCII files of, really long list of numbers. So the status quo is we can work with these many individual ASCII files. It works. It's actually a really good system, because if somebody only needs 10 ground motions, they can just download this 10 ground motions. They don't have to keep a whole large data set on their computers. What we could do otherwise is store these time series in an HDF5 file. We can either store them as string, because we've got really small numbers, and so maybe if they're small enough, maybe we could store them as string, and it would just be that much more efficient to store it. It's also a way of, if my data were strings instead of number, how is that going to be different? So it was just my way of testing a string versus a NumPy array. Because NumPy arrays is the way you would store numbers in Python, and that's in binary data. And binary data is much more easily compressible, because a 2.375 is really just one number in binary, while in string it's actually, however many significant figures you have. So they are represented differently on your computer. Now, the other thing that I want to look at is, what if I store these data in many different files? And so what I've done is I open my HDF5 file and I grab the time series one at a time in a loop, or I loop through my time series and grab them one at a time, open and close this HDF5 file. It's just my way of representing what if these files were stored in different locations, but it's the same data type, so it's both NumPy array. So the difference there is going to be in how long it takes to write and read the data if I was managing different files, as as well as the file size, but the file size shouldn't really matter too much. But so therefore, those are the metrics that we're looking at: file size, write speed, and read speed. Okay. Here's a script. It's a simple script to show you how easy it is to write NumPy data. What actually takes the most time is reading and processing these files. So the first thing you do, as I've mentioned, is you open up your HDF5 file for writing, and that's the object. That's what we're going to call it. Okay. Now we're going to go through, in my benchmark, I do for 10 files, 100 files, 10,000, and so on. So that's what the first loop. And then for each time series, I'm going to read the first 4 lines, process them, grab the number of points and the time step. So that's the metadata that we want. And then I'm going to read the rest of the data. I learned that it's most efficient to initialize a NumPy array. So this is a Python thing. You initialize it with an empty array because we already know what the size of this is because it's defined by the number of points. Okay. And so we're initializing our NumPy array, and then we keep on putting values into that NumPy array. So I'm really doing this as fast as I can when I'm dealing with NumPy data. And then all we have to do is we take this array and we put it into a dataset, create dataset. This is the key. It's going to be the file name. And then I've got this compression here. What I've learned with gzip and compression is you've got to be careful, because that only works because it requires additional infrastructure. And this is something that I could baseline if I wanted to as well here. I could benchmark it. The compression works if you've got really large data sets. If it's small data sets, maybe the extra steps of the compression may actually cost you on the performance. So as much as this shows, I think I ended up actually removing it from the Python script. So you've defined your data set, and then we can assign all these attributes. So this is the metadata, because if we're going from the status quo of using our ASCII files, we don't want to lose data. Okay, we want to keep the same performance and improve on it. So we want to keep those values, and what we're going to do is we're going to define them as attributes to this metadata. And that's great because we can actually, if we want, we can search and sort or select data sets based on these metadata. So if you want, compute the maximum or maximum absolute value of this array. And so now you've got a PGA or a maximum value that you could actually use as a query. So these attributes here are twofold. One is you're keeping the information, and two is you can use them for selecting which ground motion files you want to. So it's actually a pretty nice little thing. So if you want, you can make it crazy. You put the entire database data into here, but maybe that's not worth it. I always recommend keep the metadata in a database and then get the path of the file that you need, and then you go to your HDF5 and just grab the data, okay? I find that to be the best compromise of using each tool for what it's for. And then make sure you close your file. If you want, you can open and close this file inside the loop to test, and that's how I did the testing for benchmarking in case you have different files. So this is a simple way that it's very easy to write to HDF5. Reading HDF5 is just as easy. First, what we're going to do though is we're going to read the AT2 files so that you see the comparison between them. So this is just like before. I have to read and process this AT2 file and put the time series into an array. Then if I'm doing two tests, one is just reading and the other one is reading and running it. So then if I'm running it, I'm going to run OpenSeas with this time series, okay? And so I'm testing, it's just a good way to benchmark it. How significant is read time? It may not be really significant saving, okay? It depends on how long the actual analysis of the data takes, okay? So it's good to benchmark it. And again, this would really depend on your application. So this is how much work it is to read an AT2 file. You actually have to read it and process it and turn it into a list. And you have to keep this DT because that is the time step that you need here, okay? If you read an HDF5 file, if you read an HDF5 file, well, we've already done the pre-processing for you, right? We did that when we wrote it. So now all you have to do is read the time series, and it's an NP array, so you read it directly from your HDF5 object. Very easy, and you pretty much loop through each file, okay? This is just an excerpt of the script. And if you need to run OpenCs, there it is. Here's your time series. And here's the DT that you're reading it as an attribute. Pretty straightforward, very clean, I like coding that is clean to read and understand. And don't forget to close the file. If the data was a string, we would actually have to read it first as a string and then convert it to a NumPy array of floats. Because when you read a string and turn it into an array, it actually becomes a string of strings or an array of strings. And so you need to convert those into real numbers, into floats. So pretty straightforward, just as easy to do. I didn't mention that I wanted to check scalability. So I ran this analyses or this benchmarking for different number of files. So in this first benchmarking, I've done 10, 100, 1,000, and 10,000 files. What we're looking right now is the writing time or inverse of speed. And I'm comparing two things. One is writing to a string, HDF5 in string, and the other one is writing it as NumPy. As you can see here, now on the left-hand side, I'm plotting it as just an absolute value, okay? But it could be that this batch has really long records. What I did is I normalized it by the megabytes that I was reading, okay, of AT2 files, just a reference number so that I can normalize this. What do we see? First of all, that if we look on the left-hand side, the more files you have, the writing time goes up. Okay, this is important because if writing time doesn't go up, it means it's a strange scalability because it takes just as long to write a few files as it does to write many, many files. And so maybe this may not be the best solution if you have a small number of files. Or vice versa, it's a great solution for a large number of files. But that doesn't seem reasonable, right? But it's always good to look at this. It's always relevant to look at the plot on the left-hand side. What do we see on the left-hand side is that it takes longer to write a string than to write a NumPy. Because for every one digit or for every one number, there's actually, 6 or 7 digits that you need to write. If we normalize this, we see that writing to NumPy is scalable. Even if you're writing bigger and more files, you're not really affected in writing speed. While writing to a string, you're actually affected, and it actually goes up and down. So this is something you'd want to look into further. But most important, which is really what looking at our solution, that I know now I want to do HDF5 files with NumPy arrays because I can, because my data is numbers, okay? If your data is strings, you got to really make sure to check what it is that you're doing there, okay? Now let's look at file size. And this is, to me, it's my most important metric because I'm going to be hanging on to these files for a really long time. And I'm going to be using these a lot. And so this is something that I want to keep track of. Now, on the left-hand side, you've got the value itself. And then on the right-hand side, we've got it normalized with respect to the size of the total size of the AT2 files. So you'll see in blue, it's the AT2 files, and of course it's 1. Okay, so first we look at the left-hand side. We go, okay, it increases with file size, which is good and is expected. And then we look at normalize, and now we're saying, hey, this is totally scalable. And look at this. There's a 48% or reduction in file size. So it's totally worth going to HDF5 files using NumPy arrays. If my data was strings, then I'm not really saving that much, except for maybe you're saving in other ways, okay? But I'm not really saving in file space, at least in this case. Test it with yours and see what you get for your case. This was just a general test for me to tell me, hey, don't save it as string, save it as NumPy. So I'm satisfied with the results that I'm getting here. So write time, definitely faster. And most importantly, this is the most expensive quant metric for me, is the file size, which means now I can produce twice as much data as I did before, or store twice as much data. And so that's excellent. The next metric we want to do is look at read and run time. So on the left-hand side, we have just read time, and these are not normalized. The next slide, they're going to be normalized. On the left is read only. On the right is read and run the tiny little time series. And it's only 10 seconds of time series, okay? So it's increasing with time with the number of files, and that makes sense. And when we find on the right-hand side, this is not normalized, this is just adding a run, is we see that things are going up with the number of files. And what do we see here? That the AT2 files may actually not take as long to run as the string files. This could actually just also be a freak thing of the moment. To me, I look qualitatively, these two are in the same ballpark and these two are in the same ballpark. What this tells me, comparing the two red and green, which sometimes can be hard to distinguish anyways, is that whether I'm working with one big file or many smaller files, in the read and write, it actually doesn't really make much of a difference, okay? But this is actually, no, it's not smaller files because these two files are the same. This is just opening and closing. You'll see my results later that actually the file size does matter, okay? But this was literally the opening and closing, and there's not a significant difference, but there's definitely a difference between NumPy and dealing with ASCII. So let's normalize these. And let's see the scalability. So the read-only, this is all with respect to 1 for the case of AT2 files. And what I see, as I mentioned, especially for more files, there's definitely a performance gain in reading HDF5 files, because you also don't have to process them versus reading AT2 files that you have to process, and then these you don't have to process because you already have the attributes. And so that's the gain in not having to process it, and then this is the gain in going to HDF5 file. And then the going up is the expense that comes with opening and closing the files. So these data here are consistent, especially for a large number of data. Now, if we go over to the right-hand side, now you've got an OpenSeas run. Now you've got a processing. And so that one kind of may throw things off a little bit, just because maybe in some cases it just took more to process this than to run this. I don't know, maybe I had other things going on. But important again, see the difference, the offset difference between them. And this really tells you that, you know, as your runtime goes up, maybe these differences are going to get smaller and smaller, that they become insignificant. I was thinking that there was going to be significant gain just from the read time. And there is actually, it's a 1, 2, you know, here it's 0.1. It takes 1/10 of the time to read a file. So it's actually a really, really big saving if you're going, you know, from reading AT2 and processing those to reading directly these NumPy arrays. But that kind of gets thrown off. So if you have very little processing time, that's great. But this is a processing time that is kind of the same for all of them. Okay, so again, it depends on your application. Always important at the end of your analyses, or actually before your analyses, but I'm putting them at the end, compare the results. So I took those time series that I stored, either AT2 files or the other files, put them in at the base of a damped oscillator, and looked at the response and the shaking of this mass, and plotted it here. See, that was just 20 seconds of earthquake anyways. And so my analysis time would have taken longer if I did a full earthquake. And so the opening and closing time, it's a saving. It's a huge saving, but it's not a 1/10. It's not going to take you 1/10 of the time to run these analyses, because it's only the read time that takes up. So again, it depends on your applications. But this was really helpful to me to see, you know, the comparison between data types, between string and NumPy arrays versus, you know, dealing with ASCII files, individual ASCII files. So this was a good benchmark, and it taught me that, yes, I'm happy with the choice that I'm going to make, and it tells me, okay, I'm going to go with the green. I may learn later that I may have to go to this option as well, okay? And this option isn't costing me so much in performance. Great, I've learned something. I'm glad you made it to the end of part 2 of benchmarking HDF5, where I did the first benchmarking on data types. I hope that this video was helpful. I'm going to be uploading part 3 and 4 once they're ready, and so I would recommend that you subscribe and maybe ring the bell so that you'll get a notice to what they're up. Thank you. Bye-bye.